right, so in 24 you have one billiard ball rolling this way. Okay, its mass is 4, and its initial velocity is 0.17. Right. So the initial momentum of this ball is 0.68, and then you have the other ball here, and it's at rest, so it has no momentum. Okay, so the P for this ball is 0. This is all prior to the collision, right, to the left of that dotted line. So the total momentum, P total, on the left side is equal to 0.68 plus 0, or 0.68. And this ball also has a mass of 4. Okay. After the collision, it said one of the balls goes off at 30 degrees to the right. So this is the line of the original momentum, the line of the original travel. One of the balls goes off at 30 degrees to the right, so that's this way. So we'll say this ball went off to the right, and then this ball goes off 60 degrees to the left. Okay, then we'll say that's this ball. So we'll call this ball 1, and we'll call this ball 2. So afterwards, the momentum of ball 2 goes off this way, and the momentum of ball 2 is equal to its mass, which is 4 times its velocity in the direction of 30 degrees. And the momentum of ball 1 is equal to its mass times its velocity. And we know that this momentum plus this momentum need to equal the original momentum, which is 0.68. Because that's the momentum's conserved, and that's what was present in the system. So on this side, what we have is a final momentum that has to be equal to 0.68. And these two vectors need to add tip to tail to equal 0.68. So let's draw them in tip to tail. So the first vector, 60 degrees. I mean, this is going to look like an equilateral triangle, but the numbers will work out. So this is 4 times V1, and then 30 degrees is right here, and this ball has a momentum of 4 times the V2. Okay, so we have a right triangle. This is actually a right triangle, and a hypotenuse, and an angle. So the cosine of 60 is going to be this side, 4 times V1 over 0.68. So V1 is the 60-degree ball, so that went 2 meters per second, 60 degrees. And then this one we would use the sine function. So sine of 60 equals 4 times V2 over 0.68. And V2 is 3.5 meters per second. So those are your two speeds. Josh?
Wouldn't the velocity be 4 meters per second and the billiard balls be 0.17 kilograms? It says that.
Oh, did I mess that up?
Yeah.
Okay. Yeah, so good call. This is
4 meters per second.
Okay. And this is 0.17. Yeah, there'd be some massive billiard balls. Okay. Yeah. But then this is also 0.17. Good catch.
Thanks.
Next part there. So then this is, oh my gosh. Wow.
Oh no. My YouTube needs to stream.
My YouTube video is ruined. 0.17.
Is this the only class you're recording?
Yeah.
Oh,
Why is it best?
Alright, so you got this guy running towards his sled. And there's a sled on the ground. Okay, and then here on this side is he's going to have jumped onto the sled, go for a ride. Okay?
Oh, it looks flat.
That's probably what I'm
Now, going at, he has a mass of 60, and he's running at 4. So that characterizes his momentum. And then the momentum of the sled is 5 times 0. So how much momentum is there before the collision, before he lands on the sled?
240.
Right, a total of 240 over here. Then he lands on the sled, and now it's 60 plus 5, right? And you got VF. The total, though, is still 240, right? Because the momentum's conserved. So the amount of momentum does not change. Now, one way people were doing this, and what you would have done with only the skills you knew at the beginning of the year, were to use kinematics. And you would have found VF, right? So you would have said VF is 3.7. Then you would have done Newton's second law, and you would say, well, the friction force is -4. It's going to affect the total mass, so the acceleration is 0.06 in the negative direction. Then you would say the sled starting from 3.7 going to 0, it's accelerating at -0.06, and how much time is it going to take? And then you would use this, and you would solve for t, and you would get 60. Now, with this new idea of momentum, it's a real simple problem. So 240 is the momentum present, no matter what, before or after. How much of that momentum is taken away from friction? All of it, right? So the momentum is going to go from 240 here to 0. So friction is going to take away that much momentum. In other words, friction is going to provide an impulse to change the momentum from 240 to 0. So all it is F delta T is mvf minus mvi. The force is -4. The time is what we want. The final momentum is going to be 0, and the initial momentum was 240. Right? So we didn't even need to do this. We don't care about the velocities. We just care about the momentum. And then it's 60 seconds. And that's it. So it's a real simple problem. And you see how when we got this equation, we combined the second law with this equation. And so by combining them, we cut out all of this work that is just done right there. So does everybody see that, how it's simpler? I don't want you doing kinematics on the test. That's not, now that we're talking about momentum, that's how we're going to do it. And in the next chapter, we learn another concept that makes it even easier. We have one skater going west. That's him. How much momentum does he have? 60, right? 40 times 1.5 is 60. We have another skater going north. We don't know how much momentum he has, but we know that his mass is 50, and he's moving at some rate of speed, 50 times VI. So these two vectors are their momentum. So we need to add those together and figure out what is the total momentum present. The momentum after the collision is equal to their total mass times their speed. And it's also the same as the momentum beforehand. So that means that the resultant of the initial momentums is the same as what the final momentum is, which is 50 plus 40 times 1. So the total momentum present is 90. So that means that the two initial momentums need to equal 90 in this direction. And now, knowing that, we can solve for VI, and we know they're moving at right angles to each other. So now we need to solve for VI. So we're going to use Pythagorean theorem here. I didn't give you an angle, so it's going to be the hypotenuse squared minus one of the sides squared equals 50 VI squared. So now you got 8100 minus 3600 equals 50 VI squared. 4500 equals 50 VI squared. You got to take the square root and then solve for VI, and you get 1.3 meters per second. So if you got 0.6, I'm not sure what happened. Maybe you didn't take the square root there.
I solved out the first half of the problem on the board.
What do you mean?
First half of the equation.
You did this.
Yeah.
Okay, now what I want to show you is I did that too, right? The only thing is, here's what you did. You would have done, Josh, walk me through what you wrote.
60 plus 50 MIB equals 90. That's what I,
Okay, so it was 60.
yeah.
Let me do this here. Would be 40 times 1.5
Plus 50 times VIB
VIB.
equals 40 times 1 plus 50 times 1.
Right. Okay. And then you solve for VIB and got 0.6. Now I did the same thing. The difference being that because they aren't in one dimension, right? They're at right angles to each other. Addition here means Pythagorean theorem, right? It means add this vector and get the resultant vector. When the vectors are not in one line, in one dimension, you have to do vector addition, right? And vector addition means you got to do your triangles. So sometimes 3 plus 4 is equal to 7, right? But when we're working with vectors, a vector of 3 and a vector of 4 at right angles to each other are not equal to 7, they're equal to 5. Right? But the add still means add them, but in this case it has to be vector addition. So this is a case where 3 plus 4 is 5, because they're at angles to each other. So I'm going to give you a graph, a force time graph. That, make this 5, 0, negative 5, 2, 3, 4, 6, 7, we'll call that 8. So the mass of this object is 1. The initial velocity at time 0 is 0. Give me the velocity, sign and magnitude and direction at 0 seconds, 3.5 seconds, 6.5 seconds, and 9 seconds. Think it out for a minute and then we'll go over it. All right. 0 seconds, what is the velocity? 0. Because at rest. Now, at 3.5 seconds, we will have changed the velocity, right? And we did that because we applied a force of -5 for 1 second. So we gave it an impulse. What was the impulse from 2 to 3 seconds? Right, -5, right? The impulse was -5. So that is now the momentum, right? Since the momentum started at 0, if we gave it -5 of momentum, that is now the momentum. What is the velocity at 3.5 seconds if the momentum is -5? -5. Does anybody have a question on that? Does that make sense? Okay.
That's not 0.
What? Right, the object is at rest. We push it this way for 1 second, and we push it with a force of 5 newtons, right?
So you're not pushing it back towards 3 seconds, so you're not pushing it.
I'm pushing it this way for 1 second.
It doesn't stay there. Push this pencil for a second, it just stop.
Right? It has momentum now. It's going to keep going. It's frictionless surface. It's going to keep going, and it goes with a momentum equal to how much momentum we gave it. If its mass is 1 and its momentum is -5, then it has to have a velocity of -5. Now, starting at 4 seconds, I begin to push it the other way towards the positive direction, and I push it for 2 seconds, and I push it with 5 newtons that whole time. So now I change this momentum by how much? 10, right? Now I give it +10, an impulse of +10. That means I increase its momentum by +10. That takes the overall momentum to what? Right, +5. So P at this point equals +5. So therefore, if the momentum's 5 and the mass is 1, the velocity has to be 5. Right? Now it's moving with a momentum of 5 kilogram meters per second, and now I push it for another second at 5, so I add 5 more units of momentum to it. So now the total momentum after 8 seconds is +10. And if it has a mass of 1 and it's moving with 10 units of momentum, then its velocity has to be 10.